Tuesday.
So, we're going to start with first order difference equations. But the thing you've got to keep in mind is the book gets into loads of detail. Now, I'm going to be very, gentle with pick topics that you can handle. There's a whole lot of stuff. So, first order difference equation. There is an example in the textbook at the very first page of chapter 1. I recommend that you read it, but notation-wise, we have yt equals v1 yt minus 1 plus w sub t. Why do I call this a first order difference? So from t, we go to t minus 1. And later on, we will connect this to difference equations, and the solutions are based on difference equations. Has anyone taken differential equations?
Yeah.
Yes.
So that's a while back, but
Yeah, if you took differential equations, difference equation is sort of a discrete version of differential equations. So the solutions that we get here will look very similar to what's in differential equations. The one with complex solutions, distinct values, real repeating values, and so forth. So we call it a first order difference equation because we go from t to t minus 1.
what would a second order look like?
Patience, we'll get to that. It's 1, 2, 3, not like 1, 2. You didn't get that speed on there. 1, 2. It's 1, 2, 3. So the book starts by saying that w sub t is a scalar. That's perfectly fine, but in practice, w sub t is actually white noise. White noise simply means normal distribution mean mu is equal to 0. And the variance is sigma squared. It doesn't have to be 1 necessarily in this class. It could be 1, it could be 0.5, it could be anything. Now, where does this white noise come from? If you go back and look at the time series model that we did last time, I said, okay, y could depend on, or y sub t could depend on, say, a plus b yt minus 1 plus epsilon t. Right, from last time. Then if I use y or x, right?
No, you use X.
X?
Yeah.
Okay, let's be consistent. And the nature of the error epsilon t is that it is correlated. So this part in a regular time series x sub t is what we call the trend excuse me. Yes.
You had y if t equals a if t plus b plus epsilon.
That's fine, T. So we would have a trend component, which is simply, a linear regression line in this case. And then we have this correlated noise. So what is this correlated noise? This correlated noise right here is simply yt equals p1 yt minus 1. Does that make sense? Correlated noise. In other words, I'm trying to stick with the notation that is in the textbook. But if I want to write that in our notation, this would simply be epsilon t equals v1 epsilon t minus 1 plus wt.
Sorry, can you repeat that stuff? I'll really trying to work.
You're busy yawning.
No, just trying to work back in it.
So this is the trend part that we wrote last time. Epsilon t in a time series model is correlated. In a linear regression model, it is not correlated, it's independent. So we have correlated noise, and our objective is to take this noise and model it as a time series model.
Okay.
Right? But even after you account for correlation, there's going to be some noise, right? So this is the part that we call as the part that we can explain in terms of correlation. And that part is the unknown noise. It's completely random. It is the white noise part. So there is only so much that you can do in terms of modeling correlated noise. But no matter what, there has to be some amount of noise error, correct? Because it's a random process. We can achieve a model correlation to a certain degree, but at the end of the day, there is some random noise that is added, and we just do not know what that is. So it would be white noise and normal distribution. Which white noise means normal distribution means there are variance in the square. Does that make sense? So these are one and the same. Sometimes in some textbooks, people will start by saying, okay, this is the entire time series, we'll model it this way. But in reality, we have the trend part, the seasonality part, and then the correlated noise part. So you have to remove this out, and we are trying to model the correlated noise. Good. So the original time series will depend on those, and which will depend on the correlated noise. The correlated noise, of course, is going to correlate on the previous time point, and then some unknown white noise. Does that make sense? So we can't simply get rid of that because it's random. I can take yt, which is b1 by t minus 1 plus wt. And I can come up with something called a recursive substitution. So what would that mean? I have yt.
So the next one would be, yeah, yt minus 1.
If I pick yt minus 1, what would that equal to?
Would be
v1.
wait, it's not going to be v2.
No, still v1, but yt minus 2. Because this constant is not going to change, right? Because the first order difference equation. Good. Likewise, have yt minus 2 is equal to v1 yt minus 3 plus wt minus 2. I can keep on going. That's what we mean by recursion. We took care of the recursion part, now we have to take care of the substitution part. So recursion then comes substitution. What does substitution mean? Well, we've got y1 is equal to, excuse me, y sub t is equal to phi1 yt minus 1 plus wt. And now I know what yt minus 1 is, right? Which is in terms of yt minus 2. So I'm going to take that and plug it back in. That's good. This way you will get phi1 squared yt minus 2 plus phi1 wt minus 1 plus wt. Good. And yt now been expressed as phi1 squared. Take yt minus 2, plug it in there. You would have phi1 yt minus 3 plus wt minus 2 plus phi1 wt minus 1 plus wt. Which will give us phi1 squared times phi1 cubed, yt minus 3 plus phi1 squared, wt minus 2 plus phi1 wt minus 1 plus wt. So yt is phi1 yt minus 1 plus wt. And we could take yt and express it in terms of yt minus 1, yt minus 2. We get that. We could take yt and write it in terms of yt minus 3. Now, one may argue, well, you said that yt depends on yt minus 1. You called it the first order difference equation. So if I had yt and yt minus 2, would it become a second order difference equation? Say yes. Yeah, okay.
Could you repeat the question?
Yt depends on yt minus 1. We call it a first order difference equation, right? And I said at the beginning, okay, yt is dependent on just yt minus 1. We took that, put it in a recursion. Now I have yt dependent on yt minus 2. Does that imply that that is a second order difference equation and that is a third order difference equation?
I want to say yes, but the answer is probably not.
You're right.
Yeah.
So I want you to go back to the concept of slope, right? When we take the derivative at a point is just the slope at that point, instantaneous slope. To find the slope, what do?
Y equals mx plus b.
That's the equation of the line.
And so rise over.
Rise over run, okay, in terms of points, what is that formula? What is y2 minus y1 divided by x2 minus x1. And that is between 2 points, x1, y1, and x2, y2. And if I want to look at an instantaneous first derivative, it's the same concept, but you bring the slope really, y2 really close to y1. So slope is just a first derivative. The second derivative is the derivative of the first. Do you agree? So you're finding another change. So the first derivative simply depends on one or two time points. y1, y2. So here, yt depends on yt minus 1. 2 time points, yt minus 1. There, it depends on yt minus 2, 2 points. Here, yt minus 3 points. Excuse me, 2 points. In every single case, we are only looking at 2 points. So we are still finding the first derivative. Does that make sense? So all of these are first order difference equations. Does that make sense? Okay, so I want you to write y sub t in terms of y sub t minus 4 and see what you get. So, of course, you have to start here, find y sub t minus 3, express it in y sub t minus 4, and then put it in the substitution. So, the next recursion naturally would be y sub t minus 3 is equal to phi1 yt minus 4 plus w t minus 4. T minus 3 equals t minus 2 and t minus 3. I'm looking at the next one. Okay, so we're going to take that yt minus 3 and plug it in there. Oh.
T minus 4, T minus 2.
So 1, 2. 2 would depend on the previous one. That is t minus 3. 4, 3 would depend on, t minus 100. So y sub t would be phi1 cubed. And we're going to plug that in, so y sub t minus 3 would be phi1 y sub t minus 4 plus wt minus 3 plus phi1 squared wt minus 2 plus phi1 w1 t minus 1 plus wt. Good. Let's review. And you'll have y sub t is equal to phi1 raised 4 yt minus 4 plus phi1 raised 3 wt minus 3 plus phi1 raised 2 wt minus 2 plus phi1 wt minus 1 plus wt. Good. In chapter 3, you will see that this is what we call an autoregressive model of order 1. So that's why we're doing it now, so we can understand the process later. So if I rewrite a bit, I can rewrite this as yt is equal to phi1 raised 4 yt minus 4. I'm just going to switch the order because I want you to see something. Of course, 2 plus 3 is the same as 3 plus 2, so I can just switch them around. So I'm going to start at w sub t and put the order in reverse. P1 WT minus 1, P1 squared WT minus 2, plus P1 cubed W3 minus T minus 3. Here is the question. This happens, what would happen let's say we don't have any life at all, but we want to keep on going it like that. What do you think would happen? If they get this, there is a path.
You just switch the bottom of W and move it to the end.
I'll just switch the,
First term, move it to the end, and then add.
so if I call this to be Y, T, and I say that it depends on, say, the previous step. So, P1 raised P, something, I'll call Y T minus P, right? And then here I have WT plus V1 WT minus 1 plus V1 squared WT minus 2 plus V1 cubed WT minus 3 plus dot 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 all the way up to P1 P WT minus P. Right. I can keep on going. By all means, I can make this of order infinity. Which we will also see later on. An AR1 model is the same as an MA infinity model. You will understand as the way we get to it. So this is what we have in terms of an expression for y sub t and having recursions. Keep on going. If I
Professor,
yes.
the last one would be P minus 1.
Because you're gonna, whatever your P number is gonna be in your bottom. Doesn't matter if it's one or not.
Yeah, but at the very end, shouldn't it be?
This is T minus P, so P and P.
So I think T minus one's already.
Now let's talk about power.
And yeah, it's always the power.
It's always the power of phi. Four, 1, 1, 2, 2, 3, 3.
Okay.
So we're going to do something funky. Going back, this is what we call recursion by, expressing what say in terms of previous errors using recursion and substitution. But there is a different way to approach this. To recall yt is v1 y t minus 1 and plus wt. If I move this to the other side, I will have yt minus v1 yt minus 1 equals wt. Yes? And now the lag operators come in chapter 2, but I'm trying to show you something. Now, what is a lag operator? Your book uses the letter L. We call it lag or backwards operator. They're one and the same. So some books would use B and some would use L. Your book is using L. So what does that mean? If you have L and multiply by y sub t, you would get y sub t minus 1. Okay, one step back. It's the same as saying b y sub t would give you y sub t minus 1. Similar manner, if I did b squared y sub t, which is the same as L squared y sub t, I could write L squared as L times L y sub t. Correct. But what is L times y sub t? It is y sub t minus 1. So we will have L multiplied by y sub t minus 1. So if I apply the lag or backwards operation one more time to y sub t minus 1, what would I get?
Y sub t minus 2.
Y sub t minus 2. Keep on going. B raised k y sub t equals L raised k y sub t, which would simply be y sub t minus k. And there is a reason as to why we call lag or backwards operator. Lagging means staying behind, right? Here you're staying behind by one step there, 2 steps there, k steps, which is the same as saying, okay, I'm looking backward 1 step, looking backward 2 steps, looking backward k steps. So here I can rewrite phi1 yt minus 1, phi1l y sub t. Do you agree? And that would equal to w sub t. What do they have in common? What is common between this term and that term? Y sub t. Right? So y sub t would be equal, divide by 1 minus phi1l. One over 1 minus phi1l requires something called calculus. Suppose we have sum k equals 0 to infinity, a raised k. And I'm going to impose the absolute value of a is less than 1. And a clearly is not going to equal to 0. What would that series equal to, that sum? Come on, math guy. You should know this.
It's just A0 plus A1 plus A2 plus AK.
A0, which is 1, plus A1, plus A plus A squared, plus A cubed, all the way. So this is simply 1 plus A squared, plus A cubed, plus blah, 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 blah. Right?
I thought you said it was less than one.
A is less than 1. Right? So I'm asking you if I pick A to be 1/2. So I'm adding 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1/128. If I keep on going, what would that sum be? The infinite sum. Two. Why is that? That sum is simply 1/1 minus A. That is the sum of geometric series. Good. If I called that phi1 times L as A, this looks like the final sum about that. Correct. So I'm going to go backwards. If that's what I have, that looks like this. This came from that. Do we agree? So I'm just going to go back and reverse and replace A by phi1 L. So I'm sort of doing what chapter 1 and 2 side by side so that you can understand things better. This sum doesn't depend on t, so Wt is simply a constant, so W sub t can come out. And I know if that is A, I can write it that way. Yes. So 1 plus A plus A squared plus A cubed plus A raised 4 dot dot dot. Good. Space. So 1 plus P1 L plus P2 L squared. Excuse me, P1 squared L squared. P1 cubed L cubed. P1 raised 4 L raised 4 plus dot dot dot. I'm going to distribute Wt in. Wt times 1 is W sub t. W sub t times Phi1 times L. Phi1 is a constant. What would happen to the index t if I apply L once?
T minus 1.
T minus 1, so W T minus 1. What would happen to the index t if I multiply by L squared?
T minus 3.
T minus 3.
T minus 2 like
What would happen if I take L cubed? What would happen to that t if I applied L cubed to t? t minus 3. So 5p1 cubed, t minus 3. Of course, I can keep on going, right? I want you to look at that, and I want you to look at what we had initially, right? This part right here is the same as that part right there. Do you agree? The only additional part that we have in terms of the recursive substitution is this, right? But practically, it will make sense. Why so? Now, figure 1, in practice, once again, when we get to chapter 1, we have a restriction that phi times L has to be less than 1. L is an operator, so phi has to be less, phi 1 has to be less than 1. So phi 1 has to be less than 1. Let's say you have 1/2. And if you took 1/2 and raise it to the power of 10, would it be an extremely small value or an extremely large value? Small. Small. So that pretty much is going to go away, right? Or another way of looking at it, today's whatever observation that we made could possibly only depend, 10 days in the past, right? Today's weather, perhaps I could go 10 days. It wouldn't make sense for me to look at today's weather based on what happened last year, right? That's silly. So naturally, this part would be 0. So what we would end up saying is y sub t simply depends on a combination of all w sub t's. Whatever noise we observed yesterday or today, yesterday, day before, and so forth. And again, whatever rule applied there would also apply here. But I can't look at the noise that happened prior 100 days back in time, right? So it could probably depend all the way up to, say, 3. With me. So, all in all, what we are trying to say, so if this p is saying infinity, this is going to go away. What we're to measure today is merely a combination of noisy stuff that happened in the past, right? I always use this light example. Whatever that you are as a person at this moment, today, is merely a combination of all the random things that happened to you in the past, say, 10 days. Yes, you grow up each day and buy something. Your mind changes like something. So whatever that happens to you today as a time series is merely a combination of a bunch of things, random things that happened to you over the past 10 days, or P days in this case. Good. But you can't say whatever that I am today is purely dependent on all the way to the day when I was born. That's silly, right? Half the time we don't even remember what happened, prior to 8 years old or 10 years old. You have no clue. You don't remember everything. So what you want today can only depend on whatever random things that happened to you in the past 10 days or so. Does that make sense? So our objective would eventually be trying to find that phi 1 using delta, and that would be in chapter 3. Does that make sense? Good. So I'm starting to work on the homework, so it should be coming soon. Okay, good.